random forest and bagging pasting algorithms are solving the overfitting issue with the decision trees, right? Any questions there? Okay. So let us start understanding boosting algorithm. So we have seen the parallel processing algorithms. Here the random forest or bagging pasting or parallel processing. So you can build these models parallelly on multiple processors or multiple servers. And you can make predictions also on multiple servers and combine the result and can predict. Now the boosting algorithms are sequential. They are not parallel. So you build a model, take the result, pass it to another model, take the result, pass it to another model. Like that you do. If I say 500 models, right? There will be 500 models sequentially getting trained and the outcome is being passed. To make prediction also, you pass the record to first model, then it will predict, second model, it will predict, like that. Ultimately, all models results you combine and take it. Okay. So the boosting, originally called as hypothesis boosting, refers to any ensemble model that can combine several weak learners into a strong learner. This is an important point. Okay. When you combine weak learners and make it a strong learner, that's where the boosting algorithm is useful. Boosting algorithms are useful. What is a weak learner? Any algorithm, any model which gives you an accuracy less than 50% is known as weak learner. Right? You are using multiple algorithms, you are changing hyperparameters, still you are getting less accuracy, then you should be going with the boosting. Okay, rather boosting algorithms are not useful. How when you should go for boosting algorithms is a question. The answer is when the learner is weak. When I say learner, right, you would have tried all different approaches to make the model the best, but still the model is not working good. Then you need to build a boosting algorithm. Okay, the general idea of boosting method is to train predictors sequentially, each trying to correct its predecessor's error. So in this sequence, right, the first model may do some mistake, the second model will try to correct that mistake, third model will try to correct the second model's mistake, like that. Nth model will try to correct n-1th model's mistake. Okay. There are many boosting algorithms, but ADA boosting and gradient boosting are the ones we are going to look at. ADA boosting is useful in classification. Gradient boosting is useful in regression. ADA boosting is a popular technique which helps you combine multiple weak classifiers into a single strong classifier. A weak classifier is simply a classifier that performs poorly but performs better than random guessing. Right? Random guessing may give you maybe 10-30% accuracy, but the model may give you 50% accuracy. So that's called as weak classifier. ADA boosting can be applied to any classification algorithm. So it's a technique that built on top of other classifiers. It is like bagging, right? When you take bagging classifier can take any algorithm. Here we have taken decision tree, and here we have taken logistic regression. Like that, the ADA boosting classifier also can take any algorithm. So here ADA boosting, and I've used decision trees here, but you can use logistic regression or SCM or whatever. Okay. So you could just train a bunch of weak classifiers on your own and combine the results. So what does the ADA boosting does, especially? So it is so the difference is the approach is like this. We are doing a sequential training, right? So every time we train, the training set will change. Okay, in the boosting algorithm, for the first model, the train set is original train set. For the second model, the train set will get modified a little bit, and that train set will be passed. For the third model, the train set will be modified even further, and that will be passed as train set for the third model. It is like this. If you look at this, I passed this data, right? While passing this data, all these minuses and pluses are of same size. That means equal weightage is given. When I say weightage, right, we'll multiply with some number. Each record will multiply with some number. Maybe that is 1 by m. Think that 1 by m. There are m number of records. You took 1 by m and multiplied all the input variables, okay, and passed it to the model. Suppose the decision tree. When you passed it to the decision tree, it made mistake on these two records and this record. What you try to do is, try to raise weightage for these three records and create a new data set, new train set. Getting it right? And the first iteration, you multiplied each record with 1 by m. M is the number of records. If you have 1000 records, 1 by 1000 you took and multiplied each record with 1 by 1000 and then passed it to the decision tree model. You tried to make predictions, right? On the train set, you tried to make predictions. It made error on this record, and this record. Next time when you are going to pass it to the decision tree again, you multiply these three records with a bigger number. May not be 1 by 10,000. You calculate a number in such a way that wherever the error happened, those records are multiplied with higher number, so that the focus of the model will be high on these three records, right? When your when your row is having bigger numbers, right, the algorithm's focus will get more there because the equation will be more evident, right? When you multiply this each record with 1 by 1000, you are kind of reducing all the numbers to small numbers. But here, when you are trying to multiply these three numbers with big numbers, and when you try to multiply these three numbers with big number and the other record with a little small number, the equations of these three numbers will be more evident. The algorithm will focus more on it or try to understand pattern on those records heavily, and the error may get corrected. In the first iteration, the first model may have done a mistake, but on the second iteration, the mistake on these three records may reduce, but it may do mistake on other three records or 4 records or maybe 10 records. So in the next iteration, you try to increase the weightage for these three records where the error happened and reduce the weightage for the records where the error did not happen. That way you try to correct the error on the third iteration. So like that, you build n number of models and try to combine all those n number of models and make a prediction. Okay. So let me explain the second part also, then we'll stop and try to discuss. The classifier output weightage. After each classifier is trained, the classifier's weight is calculated based on its accuracy. Okay. So we have built 3 models here, right? For all 3 models, the weightage will be for the first model's prediction, some weightage will be given. Second model's prediction, some weightage will be given. Third model's prediction, some weightage will be given. These are ensemble models, right? When you are using ensemble models, what you are doing, either probability or the prediction you are taking and trying to make the ultimate prediction, right? Here, we will not take probability or prediction. We will give some weightage to each of these models and then multiply the weightage with the prediction they made and then sum up and take a decision. More accurately, classifiers are given more weightage. A classifier with 50% accuracy given weightage 0. If it is less than 50%, a negative weightage is given. If it is more than, a positive weightage is given. 50% is equal to 0, right? And if it is less, right, you will get a negative number. If it is more, you will get a positive number, and number is going to be between 0 and 1. Okay, from 0 to 50, it is going to be -1 to 0, and from 50% accuracy to 100% accuracy, it is going to be 0 to 1. Okay, so that way the number is given. So and all the predictions you take and multiply that prediction with the score of this predictor. All the predictions you take, multiply the predictions with the score. All the predictions you take, multiply with the score. If it is greater than or equal to 0, you say the record belongs to positive case. If it is less than or equal to 0, less than 0, you say the record belongs to 1. So ultimately the model becomes like this. When you combine all these, right, the model becomes like this, and all the blue area is predicting negatives and all the red area is predicting positives. Got it? Any questions? Got it, right?
Yes, sir. Got it, sir.
Okay. So that is simple, right? That is simple. So how will it calculate the weightage? This is the formula. Okay. Each instant weightage Wi is initially calculated as 1 by m. You multiply each record with 1 by m here, then build a model. On the second iteration, first predictor's weight alpha 1, the the classifier is calculated using the formula. So the weightage, the predictor's weightage alpha is calculated like this. So you multiply that alpha with the predictions, alpha with the predictions, alpha with the predictions, like that. So the first predictor's weightage alpha is calculated using alpha is equal to this is gamma, I think. Gamma, or I forgot, eta. Yeah, this is eta into log 1 minus r1 by r1. So how the r1 is calculated? Eta is a learning rate parameter. It's a hyperparameter. You can fine tune it. R1 is calculated like this. Sigma I is equal to 1 to m wi, where yi cap is not equal to yi. I don't know whether you can see this or not. See that, right? So this R1 is calculated like this. So on the numerator, if 3 records are, out of how many records are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 records are there, right? Out of 10 records, 3 records are wrongly predicted. 1 by 10 plus 1 by 10 plus 1 by 10, right? Wi is the weightage given to each record. Each record is given 1 by 10, right? So it's going to be 3 by 10 on the numerator, and on the denominator it's going to be 1, because 1 by 10 plus 1 by 10 plus and so on, 1 by 10 for 10 times, right? It is 1. So it's going to be 3 by 10. R1 is 3 by 10. You substitute R1 here, you will get the weightage for the model, first model. Okay, and each instance Wi is calculated. Wi is equal to Wi if yi is equal to yi cap. If the prediction is correct, right? The previous weightage is the current weightage. If the prediction is wrong, then we'll increase the weightage, right? How do you increase? Wi is equal to Wi into exponential of alpha 1. Whatever alpha 1 we calculated here. If you think the eta is equal to 1, it is going to be 1 minus 3 by 10 by 3 by 10. It's going to be 7 by 10 by 3 by 10. It is 7 by 3. It's a positive number, right? It's a number greater than 1. 7 by 3 is a number greater than 1. You put that here. E to the power of 7 by 3 is going to be a big number than 2.3, whatever that exponential is. E value is 2.37, I think. 2.37 to the power of 1, 2 point whatever, right? 3 by 7, 7 by 3 is going to be 2.33, right? 2.37 to the power of 2.33 is going to be a number, which is like around 6 or 7, right? 6 or 7. You multiply 1 by 10 with 6 by 6 or 7. That's going to be 6 by 10. You are giving more weightage to the wrongly predicted records. Got it? How are you calculating the weightage for the wrongly predicted records? I am saying that these 3 records will be given more weightage, right? This is how you calculate. Okay, and then again alpha 2 you calculate using these W's, and using these W's you calculate R2 and you calculate alpha 2 also, the weightage given to the second model. Like that, if you have n number of models, right, you calculate Now you assign weightages to records and then calculate the weightage for the model, and ultimately you take the model's weightages and then predictions and try to make the ultimate prediction. That is ADA boosting. Okay, got it? Any questions on the formulas here? Okay, step 3, 4. Step 2 is repeated until desired number of predictors are reached or perfect prediction is found. It's a hyperparameter, how many models you should be building, n estimators. And alpha you can actually play with. And there are algorithms like SAMME, stage-wise additive modeling and multi-class exponential loss function, and SAMME.R. Like, these are advanced algorithms, and I never looked into these, and I don't think there is a need also. If we know how to play with the hyperparameters, that's enough. So we have got 88% accuracy on this particular model. What is the data set we used here? What was the data set we used? Yeah, Make Moons is the data set I used. Okay, Make Moons data set. We got 88% accuracy on ADA boosting. That is ADA boosting, and then gradient boosting. So gradient boosting is useful in predicting for the regression problems. Just like ADA boosting, gradient boosting is also a sequential model. Instead of tweaking the weights, the gradient boosting looks at the error. Okay, the method tries to fit the new predictor to the residual error made by the previous predictor. So I'll write this and explain a little bit. Right? So gradient boosting works with regression or classification tasks, but generally regression is preferred. When we build a gradient boosting model using decision trees, we call it as gradient tree boosting, gradient boosted regression trees. Okay, or gradient boosted regression trees. If we look at a simple example here, we may understand. Let me show you the example first, the code example first, and then I'll draw and explain. Okay, so I have taken decision tree regressor here, right, with depth 2 and random state 32, and I fitted a model. Once after fitting a model, I am predicting, and this is y cap, right? When I predict, that's y cap, and I took y minus y cap as y2. So let me try to write it down. So gradient boosting is an interesting algorithm. Okay, so I took the data set. Okay, then I built a model, first model, right? Decision tree 1, I will say. Decision tree 1 I built. And then I calculated y cap. For each row, I calculated y cap. Okay, now I am going to build next decision tree. Before I build that next decision tree, what I am doing is, I will say this is y1 and this is y1 cap. Okay, next decision tree is going to be x1, x2, and so on, xn, y minus y cap, y1 minus y1 cap, I will take it as y2. Let me write this out. xn, y2, now the target variable we are changing for the second model is equal to y1 minus y1 cap, or y minus y1 cap, it doesn't matter. Okay, now I will build decision tree 2. So what I'm doing here, in the first model, I did some mistake, right? What is the mistake? What is the error? Y minus y cap. In the second model, I am trying to predict y minus y cap. Right? Whatever mistake I made, I am trying to predict it. What the model will try to do? It will try to predict a value y2 cap which is close to y2, right? Now the model will try to make a prediction which is close to this y2. What is y2? y2 is an error on the first model, right? What is error? The gap between the actual and predicted, right? What are we trying to do here? We are trying to correct that mistake. Whatever the mistake we did in first model, we are trying to predict, correct that mistake. If we get y2 close to, y2 cap close to y2, right? If you combine this prediction and this prediction, you will get actual y, right? Are you getting it? Are you getting it? No? Suppose that the y values are 10, 25, 30 and 15. Okay. On the first decision tree model, when I built a model and predicted, I've got 8, 23, 32, 13. Okay. So I am taking same axis, same inputs, and I am taking error as the y for the second model. What is the error here? y1 minus y1 cap, right? It is 2 minus 2, 2 minus 2 and 2. Okay, something like that. Okay. I built a second model, decision tree 2. Suppose that the y cap is 0. So y cap is 2 minus 2 minus 2 and 2. Is that minus 2? Y minus y cap is 2, right? This is plus 2 it is, right? 25 minus 23 is plus 2, right? 30 minus 32 is minus 2. 15 minus 13 is 2, right? So suppose that if if the second model, suppose that the second model is predicted correctly. Okay. Now what I can do, I can actually say the ultimate prediction pred is equal to y1 cap plus y2 cap. Ultimate prediction is equal to y1 cap plus y2 cap. What is y1 cap? Y1 cap plus y2 cap? 8 plus 2 is 10. 23. This is plus 2. This is minus 2. Sorry. 23 plus 2 is 25. Right? 32 minus 2 is 30. 13 plus 2 is 15. Right? Is the prediction correct? Ultimate prediction?
Yes, sir.
Right? That's the logic. When you are building gradient boosting, you may not get it in 2 iterations. Then what you should do? Right? First you build a model, you will predict y1 cap. The second model, you predict y2 cap. And third model, again you need to take x1, x2 and so on xn. And y2 minus y2 cap as the y value. And then try to build a decision tree 3 and then predict y3 cap, right? Like that you build maybe 100 models, 1, 2, 3, dt1, dt2, dt3, like the dt100 you build, and ultimately you combine. The ultimate prediction is equal to y1 cap, y2 cap and so on, y100 cap. Now you try to look at the error. So that is the gradient boosting algorithm. Got it? Got it?
Yes.
Okay. So we are trying to correct the mistake of the previous error and try to combine all those predictions and try to make. So here I did that. Tree regression 1 I fitted and took y2 as y1 minus y, and then built a model with x and y2. Again I predicted, right? I calculated y3, the error, That I took as the y cap for the third model. And again, I calculated y4, which is the error from y3, right, y minus y cap, and built a model. And ultimately, after building all these models, I looked at the errors here, the predicted values here. And when I summed up all these errors, right, I've got 0.57. The original value of the record is, where is the original value? Yeah, 0.59. Actual x is 0.45. Actual y is 0.59. But the first model predicted 5.2, second model predicted a little more, third model negated it, fourth model added it. So when I sum up all those predictions, right, I've got a number which is close to 0.59. So 4 models are not enough. Maybe we have to build 10 more or 15 more models where we'll get a number close to 0.59. Okay, that's how it's going to work. This is actually a way to understand. I built a simple 4 algorithms and tried to show you that when you sum up all the predictions, you get a number close to the target variable. But gradient boosting has got an algorithm already built. Right? This algorithm will have a cost function which will actually look at the error and try to adjust the models while building the model, while training the model. So gradient boosting regressor will take, I have taken a weak learner. When I say weak learner, depth 2 I have taken. When I take depth 2, right, the model will not be that accurate. Okay, and then n estimators I have taken 200 sequential ones. Now the first model will be built on y, second model will be y1 cap, third model will be y2, the fourth model will be y3, like that. Okay, so I fitted the model, and then the plotted. See here. What there are hyperparameters here. So if your learning rate is high, the model overfits. If the learning rate is low, the model actually underfits. Or if your model is overfitting, you need to reduce the learning rate. See this? Here it is overfitted, right? Do you agree? I am saying this is overfitted. Is that right statement?
Yes, sir.
Why? Why?
Because the actual and predicted difference is high.
No. Anybody else? I am saying this is overfitted. This diagram is overfitted.
The predicted graph is passing through all the data points. So
yeah, right. The predictions are exactly matching on the train set. They're actually touching. The model is actually trying to touch each data point. It will forget the generalization. When it touches all the data points on train set, it forgets generalization. If it is doing like this, right, then it may be a little generalized. In further records, maybe beyond this, whatever the scope, you may have more records on the train set and test set and production. So there it may work well. So what is overfitting? It is working well on the train set. That means every dot is being touched. When you use this line to make predictions, all the dots will be, all the predictions will be correct. But here, all the predictions may not be correct on train set, but on test set, it may actually generalize. So what is overfitting? What is regularization? We are trying to reduce the accuracy on train set so that it works well on the test set. Got it? We are trying to smoothen the curve. This curve a little bit smoothened, right here. Agreed? Agreed, right? Yeah, that's the point, right? That's the point you need to understand. And one more thing is, we are using decision trees. And in the previous classes, I said that decision trees can do blocks, regions, right? Region 1, region 2, region 3, like that. But here it is doing curves also, right? When you use these kinds of what you call it as random forest bagging, pasting, or boosting algorithms, decision trees also can do curves, not just straight lines. Okay. So the learning rate, when you increase, overfitting increases, learning rate, overfitting decreases, and you decrease learning rate. That point is enough. Right? When you build a model, you need to understand how to play with the hyperparameter. We understood hyperparameters and how whole math on gradient descent because the gradient descent algorithm explains you on, gives you a clear picture on how the learning, the hyperparameters work. One thing. Second thing, in deep learning, we'll use it. Deep learning's basis is gradient descent. Okay, so that's where we learned there. But here I am not focusing much on how the algorithm is working, because it's waste of time in my view. Right? When you have to build a model, if you know how to play with the hyperparameters, that's good enough. So we know what is overfitting, what is underfitting, what happens when you increase and what happens when you decrease. That's enough, I think. Okay, with that, right, we're almost at the end of the machine learning course. You guys can create, start doing your resume. Right? Maybe in a week you can prepare your resume and put it. Anyway, it is coronavirus time and openings will be less, but be prepared. Maybe by month end everything gets settled and we may have our normal life as it is. Okay, so I will stop the class for today because if I start the anomaly detection, right, I may not be able to finish it in maybe 15-20 minutes and it's going to be hurry also. So tomorrow we'll start anomaly detection. I'll explain anomaly detection and maybe Friday we'll start the NLP concepts. I'm thinking of doing NLP with machine learning first and then deep learning and then NLP with deep learning.